Hello and welcome again to my Physics Online video lecture series. Today's video we're going to be talking a little bit about the Bohr model of the atom and to some extent the Rutherford model of the atom. So up to this point we've had an overview video in which we've discussed a few different historical models of the atom, what the atom was thought to be, and some of the experiments and development of this model. Today I wanted to focus in on the sort of two models that transitioned from the really classical atom to the more modern atom. So the main model obviously is the Bohr model. That one came after the Rutherford model. So what was the Rutherford model and why did it come to exist? Well, Rutherford had done his scattering experiment, and so Rutherford basically shot alpha particles towards a bunch of gold atoms, and then saw what the scattering angle was. So what that basically did was that from the previous model, the plum pudding model or the Thomson model, the result should have been that these alpha particles travel in, they interact with the nucleus, and they scatter at relatively small angles like so. So we have this beam coming in, and then we have scattering angles like this that are predominantly small angle scattering. So this is existing model. This is the Thomson model. The observation, however, involved shooting these alpha particles at this nucleus, and then yes, we did still see a lot of scattering at small angles like so, but there were occasional particles that scattered at very large angles like so. So prediction, small angle scattering only, whereas in the experiment all angles were possible, although most scattering tended to be at relatively small angles. So the Rutherford basically what he concluded was that the positive charge is located in a very small region of space. This would be the atomic nucleus, which has a radius on the order of maybe a femtometer or a few femtometers. And then the electrons must orbit this. Thus, we get sort of like solar system style orbits where you have a positive nucleus and then an electron basically orbiting, much like a planet orbiting around the sun. So we have some elliptical orbit like so, or maybe even a circular orbit. So what was the problem with this? Well, in order for this orbit to occur, you have this electron that is moving in some direction and it's turning. Okay, so we have a V, and then sometime later V is in some other direction. Whether it's sped up or slowed down, V has changed direction, and that means that we have some center-seeking acceleration. So this basically means we would need to have centripetal acceleration, and classically, if you accelerate a charge, you get radiation. Emitting radiation everywhere, the result is that it should be losing energy. And to lose energy means to basically lose orbit. And so basically what we would expect to have happen is sort of like this little simulation that the people from the Colorado Fed have put together. Classical solar system orbit. If I were to play this out, spirals in and eventually collides with the core and that's it. Your electron has moved into the nucleus, and your atom is now sort of like broken. So this would happen over and over and over again. In some sense, the Rutherford model was the last of all these models that might be called a classical model. He had contributed this idea that there was a nucleus that had positive charge and that electrons orbited this nucleus. Bohr made an intuitive set of leaps. Basically, his intuition says that there's some quantization for the electron. So electron energy and angular momentum are quantized. So this is like the first step into quantum mechanics for the atom, for models of the atom. This is sometimes called a semi-classical or part quantum, part classical, because the orbits, other than not radiating and other than being quantized in what values they have, these orbits basically are classical. It's just they're fixed. There's like a fixed radius, a fixed energy level, a fixed angular momentum. So the energy levels are fixed for a given atom. The angular momentum that you can obtain for an electron is fixed in basically multiples of what's called Planck's reduced constant. And so the Planck's constant is already known. Planck's reduced constant we represent by h bar. So h bar is defined as Planck's constant h divided by 2 pi. So with this in mind, in the Bohr model, the angular momentum L, which as you know is classically m times r times v, is given by n, some multiplier, times h bar, or if you prefer, n times h over 2 pi. So in some sense, this dictates what the combination m times r times v must be equal to. And now classically, you know that we know what the mass of the electron is. That was measured essentially by Thomson and Millikan. Between the two of them, Thomson did the charge to mass ratio experiment, and then Millikan actually measured the charge of an electron. So we know what the mass of an electron is. That means that R and V are collectively fixed somehow by this quantity. And then we go back to the Coulombic potential, and we know what kind of force is allowed coulombically. This essentially fixed values for how far away from the atom's nucleus could this thing be orbiting and with what speed. So if we apply Coulomb's law, where this force from the Coulomb is also the centripetal force, we would have the Coulomb constant times the charge of an electron times the charge of the nucleus divided by basically like the radius of the electron's orbit, which I'm labeling as RA for atomic. Now obviously K Coulomb is 1 over 4 pi epsilon naught. The charge of an electron, we use the fundamental charge. Charge of the nucleus is however many protons are present in the nucleus times the charge of a proton. And so this basically ends up giving us the radius of the orbit, because we also know that Fc classically must be the mass of the electron times the speed tangential squared divided by the radius at which that speed is. This is using centripetal force. So if you put these two together, you can solve for what the atomic radius must be equal to. So this is the atomic radius of a generic atom within positive charges in the nucleus. This does not account for things like the possibility of shielding. So if I have two electrons that one is closer to the nucleus than the other, then the effective force is maybe smaller for the second one than otherwise would be, because there's a difference in what kind of total charge it sort of like sees. In this case is called the quantum number. So this is sometimes referred to as principal quantum number. And it is some integer. So n equals 1, 2, 3, etc. This n right here is number of protons in nucleus. Protons being the positive charges in the nucleus. The rest of these are fundamental constants. This again is your permittivity of free space. And of course you know that one to have this value of a little less than 8.85 times 10 to the minus 12 farads per meter, and then the mass of the electron and the elementary charge. You can therefore do two things at this point. So in some sense this is your radius of your atom in general. One thing is you can now figure out what are the allowed speeds. So V sub n, your allowed speed, would be 1 over this permittivity times the sort of like charge divided by 2n times h. Okay, so that is how fast the electron that's making this particular orbit should be traveling classically. The other is we can estimate for a hydrogen atom. For a hydrogen atom, there's only one proton in the nucleus. There's also only one electron present. And so what that means is that we can kind of figure out what is the radius of this atom in terms of this principal quantum number. So you have epsilon naught n squared, that's little n squared, h squared, divided by pi times the mass of the electron times the fundamental charge squared. And so now we say, okay, what if it's in the ground state? So ground state has n equals 1. This is sort of like your fundamental hydrogen atom. So this is sometimes called the Bohr radius, and actually is often labeled as R sub A. I'm going to label it R sub B for Bohr. Basically you end up with epsilon naught n times 1 squared, so that part goes away, times h squared divided by pi times me times e squared. And so this Bohr radius comes out to about 0.5293 times 10 to the negative 10 meters. And again, a lot of sources will just label this as RA, sometimes R1. I'm labeling it RB for Bohr, since I already used RA for atomic. One thing to note here is that this is roughly 0.5 times 10 to the negative 10. The nucleus, we said earlier, was about 10 to the negative 15. So the atomic radius for the smallest atom, hydrogen, is still roughly 4 or so orders of magnitude larger than the nucleus, almost 5 orders of magnitude larger than the nucleus. Let's have a brief example to help wrap things up. we figured out what the radius is for the Bohr atom for the ground state hydrogen. The other half is what speed should the electron be traveling at. So this speed, basically V1 for hydrogen, you should use 1 over epsilon naught times this fundamental elementary charge squared times 2 times the state, which we just said was the state number 1, times h. Okay, so elementary charge is about 1.60 times 10 to the minus 19, and we got to square that, and then we're dividing that by 8.85 times 10 to the negative 12 farads per meter. That's your epsilon naught, times 2 times h, which again is 6.62 roughly, times 10 to the negative 34 joule dot seconds. So what does all of that give us for the speed? Oh, out comes the calculator. So 1.6 squared divided by 8.85 divided by 2 divided by 6.62. So this would give us a speed of about 2.184. So let's call this 2.2 times. So that is already times 10 to the negative 2. We've got 10 to the 19 squared, so that's 10 to the negative 38 plus 2 is 40. Okay, minus 12 means we're at 10 to the negative 28, and then minus another 34 means we're looking at about 10 to the 6th meters per second. So this right here ends up being our speed for this ground state hydrogen. Good news about this number is that it is below the universal speed limit. That's a nice double check. So this is a reasonable-ish result, at least according to classical and general relativity. So what went wrong with Bohr's atom? Well, for one thing, he kind of made some intuitive leaps, but there wasn't anything to give as basis for it other than that atoms don't tend to radiate unless they're excited. So if you shock an electron to a higher energy level and it drops, then it can radiate, or if you send light into it so it absorbs and jumps up and then wait for a little bit, it will re-emit in other directions. That works out okay. And the problem is this was it didn't take into account certain other things that we later learned. For example, de Broglie posited that there's some uncertainty in the position, and Heisenberg, who's a Bohr's student actually, posited that there must be some uncertainty principle applied to the nucleus and to the electron. Now, to the electron itself, not necessarily too big of a problem, a little bit of a wiggle. To the nucleus, a little more wiggle. And so this simulation actually lets us look at some different changes in these models. So the Bohr model, here you have this single electron rotating about the hydrogen atom. You can maybe excite it to a higher state, and then as it falls to lower states, it emits, which is not a problem there. So here we've had it jump to a higher state by absorbing a photon, then as it drops, it emits some photons. So here it's emitting a couple photons. Let's go to a slower motion to catch this one more time. So here it's jumped up to a higher state, and if you watch, when it falls to the lower state, a photon gets emitted. So there it fell to a lower state and emitted a photon in a random direction. De Broglie suggests that the nucleus should have some uncertainty in its position, and as should the electron, and therefore in some sense this electron is somewhere within this kind of blue colored ring, which is wobbling up and down because of the fact that this nucleus is also wobbling. And moreover, you're not only getting the wobble of the nucleus, you're also getting the wobble of the electron about its orbit. And so you have something like this. And this was a slightly more quantum version. We've incorporated some uncertainty. Schrodinger's equation and Schrodinger's prediction modified it further to the electron existing in a probability cloud like so. So this blue cloud about the atom, that's your probability cloud. And if we excite it, then that probability cloud basically ends up sort of changing. So there's an excited and there's an excited. Let's get one more. There we've got it excited to a higher orbit. If I switch to the Bohr, unfortunately this sort of demotes it. But you can see the numbering down here actually shows the excitation to a higher state. So here we're in an excited state. Now we've emitted a photon. That was actually stimulated emission in that case. And so on. So here's a excited state. This one happens to be the fifth excited state. We have some orbital angular momentum in sort of like the first excited state of that. And we also have a z component to that orbital angular momentum is basically how you read these numbers down here. Don't worry too much about those numbers. They're kind of beyond the scope of our introductory course. All right. Now if I turn off the light source and let it keep running, there it's emitted one in a random direction and fallen back to the ground state. So that's the Schrödinger model. Again, the main thing that we're looking at here is the Bohr model. What I should note is the other thing that the Bohr model has added, kind of a fundamental contribution. First is that electron and thus atomic energy is now quantized. That's a big one because what we actually observe from a given atom is specific values of electromagnetic radiation that that atom will emit or absorb, meaning experiment shows that these should be quantized, and now this kind of explains that it will be, and predicts exactly what values a given atom should emit. Okay. The electron's angular momentum is also quantum. The other major thing that this model contributes is what causes radiation. So electromagnetic radiation occurs when a bound electron changes energy levels, not when it is accelerated. Thus, centripetal acceleration doesn't cause radiation. That's also important because that's a break from classical predictions which say that if you accelerate a charge, the charge will radiate. That's the classical explanation for how an antenna works, for example. How do you make electromagnetic radiation via an antenna, half-wave antenna? So it's not accelerating the charge that causes the radiation, it's changing the charge's energy. And these two things together kind of predict that your atomic emission should have individual lines in the spectra, not a continuous source of radiation. So you might see a red photon, you might see a blue photon, you might see a green photon, there might be an ultraviolet, but you shouldn't see like white light from red all the way into violet continuously emitted from this thing. So those are the main contributions of this Bohr model, and that's all that I'm going to do in today's video. Hopefully you found it interesting, and learn something from it, and as always, thanks for watching.